Alright, everyone. So today we're doing a the part 2 to the modern Fortran for scientific computing tutorial series. Last time we did an interactive tutorial where people followed along in making the Fortran programs that we made. We covered quite a few things, like just the basics, and a couple of things that are unique to Fortran. We'll be seeing some of those things again today in our extended example. But first, we're going to illustrate that Fortran is a modern language because it does have features for object-oriented programming. So we're going to use a toy example to illustrate some of these principles, but then we're going to start an extended example, which will be like a non-trivial scientific computing example. So you can tell it's non-trivial because the associated paper reference was written in 2016. So the example is the Lanczos method for estimating the density of states, or the spectral density of matrices. And this is real big in scientific computing. If you've ever taken a condensed matter physics course, you'll have seen the term density of states. Even if you've taken a statistical mechanics course, you'll probably have seen the terminology density of states. Now, estimating the eigenvalues of matrices has a variety of benefits. I won't go into it really. We're going to implement a couple classes, a Lanczos hammer class and a sparse matrix class, which will have its own matrix vector multiplication routine. So the Lanczos hammer class will initially work with dense matrices, so quote-unquote regular matrices, and we'll get the algorithm working, and then we're going to implement the sparse matrix class and get it working on sparse matrices. So the reason being, algorithms like this Lanczos density of states approximation algorithm are most useful with really huge matrices where you can't diagonalize them, because that's a very expensive procedure. But when you're working with really big matrices, it's not just the CPU time, the number of operations that matter. It's also the amount of memory you have available, which is why, you want to also implement or use sparse matrices. So let's start the toy example. You'll note I have a file called personmod.foate and a file .personuse.foate. If we look at personuse.foate, that's this agenda. I'll delete it. And you can type in for yourselves the program name and end program. Then we also have another file, personmod.foate, where I haven't done anything really yet other than make the module, declare implicit none, and here's a reminder of what we can do inside modules, or like what the structure of modules is. In this top part of the module, we can declare parameters, variables, types, which are what we'll cover. They're known as classes as well, interfaces, etc. And recall that a module is separated into its variable declarations, as well as interfaces, and its functions and subroutines. So let's get started. First, we'll cover how to make our own types, aka classes. So here's how you write a person class. You just define the type that you want, and of course, with any construct in Fortran, end type. Vi asks any notable difference between .f90 and .f08. To the compiler, usually no. So .f90 is the usual Fortran file extension, even for like more modern Fortran standards. But I decided to type .f08 just to make it clear that we're working with a more modern, like, Fortran standard. But for the purposes of today's seminar, there will not be any like difference to the compiler. And that's because .f90 will compile like Fortran 2008 code. All right. So what kind of properties will a person have? They'll have, for example, a name with, we'll have a fixed length name. Now, we could just leave it there, and we could go on to other properties like age. However, we can also put in default values for the properties that a class or type has. So here we have a default name just called default, and a default age being 30. Now we don't need to put in defaults, so we can put defaults like this, but you don't need to. What will happen is that when a programmer makes an instance of this type, this person type, they will initialize these values, but they don't have to initialize them if they're defaults. Type syntax. So I'm not sure what you're at the declaration level. Right. So what we're I will reference then. Now that we've declared what this type should look like, we can go to our person use file where we're going to use this module. Type person. Jacob, I'm not sure what you're saying. That is correct syntax. We can go here to our other file using this module. We can use, let's see, what was our other file called person mod. It was just people. Okay. So use people, and let's specify only person. So what this does is it tells the compiler to only bring in the person type / class from this module. So this is a little Fortran functionality that we didn't cover last time. So when we want to declare the program variables, how we would actually declare initially declare a person type is we would say type person, person1. Now, this will use the default values. We can also make another person, person2, where we pass in our own values. So Bob 25, and this passes in the values that we for the name and the age. Now this is perfectly acceptable syntax, but it's not good syntax. It's much better to write out what exactly you're initializing what to. So it's better to write out which objects you're initializing. Choose your own values. Okay. So we can do a test. For example, we can print out to the console person1 and percent name. So the percent sign is how you access the objects or the quantities within the type. And we can verify that person2 also had a name. And let's just try that. We're going to exit Emacs, and we're going to compile what we have so far. The person module and the person use. Let's see. So for debugging, remember to stop it to start at the top of the debug chain. Missing generic specification and used statement. Okay, so we have person in caps here, and why don't I just show off that Emacs can use multiple windows in one. Let's see. Curious. So it was complaining about this, I believe. Expected another dimension, an array declaration. Ah, I understand. Okay, so I had a little syntax error. What we need to do is, for initializing to particular values, you need to use this syntax. You declare person2 equals a type or class person, and then in the parentheses, you'll write the initialization values you want. So let's try that out, and voila. Let's clear the screen. Voila. We'll verify that we have an executable. Let's try it out. And their names are printed. Okay. Looks like that is all good. We can also print out the age. Let's try that. Voila. The first person, we still printed out the default name. The second person, we can verify that we set the age to 25, and that's what was printed here. All good so far. Yours still doesn't compile. If you want, you can share, like, no implicit type. Let's see. So, I think I made, let's see. Okay, so that works. All right, Jacob. Earlier I had an error with the only specification. You should only use 1 semicolon, not 2. Try that. I made the same error last time too. All right, so that all works. Great. So now let's go back to extending or learning object-oriented programming. Okay. So the person class might want to have certain procedures, like functions or subroutines, associated specifically with that class. How you specify these things is you put a contains specifier inside of the type that you make. And what we're going to type in here is procedure. Let's see. I want to make sure I get this correct. Pass self greet. So this pass, let's see, procedure tells the compiler that this is going to be a function or subroutine that we'll write out later. Pass says that you are going to automatically pass self into this procedure that we'll call greet. So what this does, automatically passes the instance of person to greet procedure. Now, let's go to the contains part of the module and implement this type-bound procedure. So, writing it like this has made this a type-bound procedure. Here we're going to make the subroutine greet. More like Fort Walked. Funny aloof. So greet, we don't need to specify any additional arguments because it's already automatically passing itself. But we do want to specify whether or not we are modifying ourselves. So we are still going to write out the type of self and whether where it's input, output, or both. So here we actually put person intent in self. So instead of class, or instead of type, we're going to write class. And this tells the compiler we only use self as input. We don't change any quantities. Now, all we're going to do in this subroutine is print something like, hi, my name is self%name, and I'm self%age years old. Yeah, actually, it was also my bad. Jacob's mistake, but we've corrected it. Okay. So, we've made a subroutine called greet that is type bound to the person type. I will keep some of this up. Right here, but then in this second Emacs window, I'm going to open back up the main program. So now, instead of these print statements, I'm going to delete them, and I'm going to instead call person1%greet. So greet is not a variable of person1, but it's a type-bound procedure. Since the procedure is associated with the person class, we can still access it with the %sign. Similarly, we can greet with person2. All right. Let's try this out. We are going to exit, recompile, get some errors, of course. There is this top error. Procedure greet with past self has no argument self. What dumb did I do? Let's look at it. Person mod. Okay. So, if we type in self here, unlike what I said before, if we type in self, we will be good. So we will actually write in the self variable in the subroutine statement, as well as the variables. The only place where we don't put self is when we actually call greet. Yeah. So let's try that, and it compiles. Let's clear up the screen, hide the errors, and voila. Now you'll notice there's actually like a bunch of extra white space on the screen when we're printing these things, right? So one of the nice things that Fortran has automatically is this thing called trim. Trim. So this is an intrinsic procedure that acts on character arrays, and it just trims out all the like extra white space. So making this change and recompiling, rerunning, and we've trimmed out the extra white space from that string. You love it, Jacob? Oh, man, I'm sorry that I fixed it. Is name a reserved variable? No. Name is what we defined up here. So we made this variable name as a quantity associated with person. Highlights it differently from age. I don't think it's a reserved variable. I mean, does it run correctly for you, Jacob? Good. If you're worried, you can change it to something else. Okay. Now, there are a few other things. When you make a class like this, you can also have private and public variables and procedures. So all of the highlights of object-oriented programming. To make an example, someone's religion, they might want to keep it private. So let's have a default value of agnostic, or better yet, unknown. And what we'll do is we'll add the private modifier to this. And what this means is that programmer can't access this directly with person% religion. And what we have to do is, if we want the person to, tell us their religion, we have to make a specific procedure for it. Pass self, tell religion. So, for syntax purposes, the contains statement can contain multiple lines of this procedure, pass self stuff. We can quickly make a subroutine for telling religion. Class person, intent in, self, and it'll just print my religion is, we'll trim it, self percent religion. So in order to actually see this, we're going to go to our main function here. Let's see. Right. Yeah, so the reason that you got that error is because you guys typed that. So the trim works on strings, and what I've written here, age is an integer. Now, if you want to remove the white space from this line, you'll have to do one of a few things. You could convert this to a string or to a character. You could make a fancy IO, a fancy like IO variable. I forget what they're called. But I'm going to let you guys look that up because those things aren't like the interesting part of Fortran. I find them kind of boring. Even the trim like wasn't necessary. It was just easy to use. So I used it here. But like the text was still perfectly readable with the extra white space. Okay. So let's you'll note that if we want to initialize the first person, we don't need to initialize all of the variables. Maybe we only want to initialize one of the variables. From what I remember, we can do that. Call person1 percent tell religion. And let's try this. No? You don't like it? Haha! So, the reason that we can't just initialize the religion variable is because we specified religion is a private component. Let's see. So let's go back to our type here. So it turns out while religion is private, we can't have the user, aka the programmer making this file, we can't have them initialize it in this way. I believe this initialization, like the empty initialization, will still work though. Let's try it out. Yeah. So the fact that the religion is private means we can't just arbitrarily access it. That includes both reading and writing, which is why the initialization I attempted didn't work. However, you'll note we still have been able to print out this religion. It just so happened to be the default one that we specified here. Now, if you're not familiar with object-oriented programming, this will mean nothing to you, but if you are familiar, this tell religion is an example of a getter method, and we could make a setter method that sets the religion of the person. And the purpose for these sorts of constructs in object-oriented programming is to separate. So the purpose of getter and setter methods in object-oriented programming is to separate the class like innards from what is visible to a programmer who's using the class. So yeah, in order to actually initialize the person's religion, we will need a setter. So let's try that. Subroutine set religion self. I'll just copy this line, and we will print, or sorry, we will set religion equals, I don't know. Here we go. So we need a few things. Set religion is going to accept a new religion. Going to have a character array with intent in new religion. Now, this first piece of syntax specifies that the self, the object, is both an input and an output, which means you can basically do anything you want to it. The second here, so this is input/output variables, and now we have the main part of the function, and we're going to set the religion of this object to the new religion that the user specified. This seems kind of odd because of the triviality of this example, but these sorts of examples are what are normally used for introducing object-oriented programming. So let's try changing our person using program. So let's call person1 set religion, and now we set it to like atheist or I don't know, Catholic, whatever you want. And when it tells religion, it should tell us Catholic. I forgot to type in new religion equals Catholic. Let's try that. I understand the error. Okay. So we need to bind the subroutine to the class. procedure, pass self, set religion. Once we add this to the person type, then we will be good for that, for the purposes of fixing that error. Let's double check. And everything compiles. Let's run a.out. Yep. Person default now has the Catholic religion. Jacob thought he did something wrong because it compiled. Okay, so as an overview, the thing we changed was we made sure to bind this subroutine. Inside this person type, we bound the subroutines set religion and tell religion. We bound those subroutines. We specified, or we implemented those subroutines in the rest of the module. So tell religion and set religion, we implemented these subroutines in the tail end of the module. And in using this class, we called those procedures set for these classes and managed to set this guy's religion. Okay, so there's a lot more to object-oriented programming. Let's go back to the module. This is the module. And we're going to do one more thing with this trivial example before going on to our non-trivial example. We are going to make a derived type, or if you like object-oriented programming, like an inherited type. Here, it's called an extended type. We're going to make a type that extends the person type, and we'll call it the woman type. Now, this woman type will inherit all of the person variables and procedures automatically, including, defaults. Now, what's different about a woman? Well, women can give birth, and so we will say that they have, a number of children equals 0 by default. And we'll have a procedure called give birth. Thanks, Packing 2. Okay. Now, the intent of the give birth procedure is just going to be to increment the number of children. Now, we can write this subroutine give birth with self. And so we will write, instead of class person, we write class woman. Intent in self. And all we're going to do is actually, it's not just intent in, it's intent in out. because we'll be changing the woman instance. So we'll have self num of children equals the number of children plus 1. So you'll note on the left-hand side, we're assigning this variable, but on the right-hand side, we're accessing the variable. That's why we need both an in and an out specified. Give birth to twins. Yeah. Jacob, I see you are... Flynn. Welcome. So, to answer Flynn's question, the procedure specifier is basically to say that this will work for either a function or a subroutine. Like we covered last time, in Fortran, you can have both functions and subroutines. And to be honest, I don't know why they go with the terminology procedure to encapsulate both instead of just writing one or the other, depending on what you actually implement. But yeah, it's convention. I agree, Flynn. It makes sense to be specific. I mean, we can try it, but I believe we'll get an error. You can try it for yourself. Replace procedure with subroutine, and let us know if it compiles. Yeah. Okay. So we'll have the woman give birth. And when we're using, we need to do a couple things. We need to make sure, one, that we're also using the woman class. 2, we need to make a woman person. Person 3 equals person whose name is, say, Jill. Well, we don't have to give her an age, so let's not. Just to illustrate that we don't need to. And we don't need to initialize her number of children. We can, though. So let's say that she already started with number of children equals 1. Now, we can tell her to give birth. We can print out person 3 name has person 3 num of children. And let's copy and paste this down here so that we can look at their number of children before and after giving birth. Does using only woman make the whole thing fail? It will make the person's part fail, I believe. But feel free to try it. I'm probably going to get errors of my own, so let's check it out. We recompile. And, yes, I did have an error. So I used the person initializer instead of the woman initializer. So let that be a lesson to yourselves. when you're making a type, you want to use the right type initializer. And when we fix that, and we fix my printing errors, remember your commas, everyone. Remember these commas too. When you fix all those, then it compiles just fine. The woman inherits the person class. And we can see, based on the running of the executable, that Jill has 1 children and then 2 children. All right. Great. Any questions so far? Yep. So you need to make sure to, when you're using the parent class, to also include the parent class in your file. Can you show the set religion function? Yeah, of course. So here's our set religion function. I like how Aloof is saying Fortran is a bit old-fashioned while we're covering object-oriented programming, a fairly modern construct. So Vi, if you're just what woman, it's not a person. But yeah, Vi, okay, cool. When you use class person and when you use type person? Good question, actually. So that is an excellent question. Let's try putting in type person. Right? Let's put in type person. Let's try compiling. Does not seem to work. And that's because the type is non-polymorphic. So what does that mean? So you use class. Here, I'll type it out. When you use class, you specify that this procedure, subroutine, works both for the person type and any types extended from it. Now, admittedly, I am not sure if there's a way to write a type-bound procedure, such as like set religion, that works only for the parent class and not for the children class. But I don't see a situation where you would want that anyway. Generally, the parent classes have fewer procedures, and then you make new procedures in the children classes or the inheriting classes. I believe a lot of what I'm covering today is originally started in the Fortran 2003 standard. So can functions be defined inside class, or must they be defined outside? Right. So this is when we're declaring the so let's see, you're asking, can we define them fully inside the class, or must they be defined outside? Let's try it. So instead of this being here, let's put it right here. I'll try it real quick. You guys don't have to copy me. And Fortran does not like this. Give birth must be a module procedure or an external procedure with an explicit interface. Right, so that line is telling us that the subroutines associated with the types have to be implemented in the contains part of the module as a whole. All this part of the type is saying is that we are declaring that the procedure defined below is bound to this type. So you always, so this is the module level contains, and this is the type level contains. We don't implement the subroutines here. We just specify that whether they're bound to this type. Does that answer your question, Vi? Cool. Yeah, Jacob. That's like the only construct I can think of that doesn't have an end counterpart. Well, I mean, it kind of makes sense, though. Like, if, then, else, and if. The else part also doesn't have an end else. But yeah. So we've seen a few object-oriented features of Fortran. There are actually a few more that I'm not going to cover. There's something called infinite polymorphism in Fortran. You can also make pointers that can point to either a person or the classes that inherit from person, and you can like change that. And there's a few special like constructs in Fortran 2003 specifically that deal with that, but I'm not going to cover those advanced object-oriented features here. This is like the basics, and that's probably more than enough for our extended example. So That's it for the trivial toy example. Does anyone have any questions before I move on to the more non-trivial example? Does have composition like the others. Let's see. Oh my goodness. What even is composition? Instantiating classes within classes. Ah, yes. Yeah. So, like you could have. Do you mean like, so within this, thank you, actually. So, for example, we might have a husband which has a default. Maybe we do name equals none by default. And let's see if this compiles. It does. Interesting. So this is what you mean, right, Jacob? Instantiating classes within classes. Yeah. So, we've established that this works. You just reminded me, Jacob, of one other thing that I wanted to show. For the giving birth procedure, let's do one other thing. Let's add in one more variable, and we're going to show off intent in. We're going to show off optional arguments. Optional arguments can be present or not. So here's the main part of our procedure, and here is the optional part of our procedure. Can we define our own constructors? Flynn, yes, you can. I'm not going to go over that, but you can. If you'd like, I can point you to some resources about it. Okay, so the optional procedures. Now, this isn't object-oriented programming. This is just like another Fortran feature. We're going to say something like, if present father, then print the father, trim the name of the father, is present at the birth. Else, print no father in sight. And if. And as a reminder, we can name these constructs. Funny Jacob. Okay, so this is one of the fairly useful features of Fortran, the fact that you can have optional arguments. I don't even think you can do that in C or C++. I don't know modern C++, so it's possible that optional arguments are a thing now, but with like the templates and stuff. But definitely in C, I don't think you can use optional arguments. Okay, so there are default arguments. Okay, so the key things are this present intrinsic will tell you if the user specified the father variable when calling the give birth. Let's illustrate this functionality by saying person 3 is giving birth, and let's say the father is person 2. And let's even have them give birth again, but without the father there, just to show it off. Okay, so let's try this. It compiles. Wow, no errors for once. And we run it. Voila. The father Bob is present. And then the second birth, no father in sight. Quite sad. That is true, Flynn. The Fortran Standard Committee will be meeting to discuss default arguments soon enough. Now, there's kind of a workaround, right? But yeah, it is kind of messy, like you're saying, Flynn. You like define a local variable. Symbol is not a dummy variable. So, I believe you're missing the fact that I added this right here. A second, like, self, comma, father. Okay. Okay, now that was it for this toy example. Anything anyone wants to bring up? Very true. Very true, Jacob. And yeah, the father especially is a dummy variable. While we're doing this, actually, let's see. So, do we want to talk about that? No, we'll talk about that later. Okay. I see Flynn is typing. I'll wait to see what you have to say. How do people usually do plotting? Yeah, that is one of the weaknesses of Fortran. There currently isn't an easy way to do plotting. There is a package you can use that basically allows you to use GNU plot from within Fortran. But what I do in practice is write to file and use Python or something. But there are people, or compiled languages have bad plotting. I mean, yeah. Well, Jacob, root isn't compiled. It's got a REPL. Just kidding. Yeah, and Fortran has a wrapper around GNU plot. I think there are some, well, not by default, but there is a package you can download that is a wrapper to GNU plot, I believe. But there are people trying to get a standard library for Fortran that will include, matplotlib-like plotting, among other things. Yeah, there's already an implementation of part of a standard library up on GitHub for Fortran. But the standard committee hasn't, any packaged database for Fortran. Oh. So people are working on the Fortran package manager. I'll fpm Fortran. It's this, and I believe you can install it with Conda or pip or something. There's a YouTube intro to using it, I believe. Let's see. Yeah, this guy called Everything Functional has got it, an intro. Or if you look at Fortran Con. Very true, Cronum. Very true. It's very recent. Yeah, it's written basically in Python. But, I mean, do whatever you need to do to have a standard package manager. Whew. Okay, so I'm going into a new directory called Lanczos, where we will try and make progress on this Lanczos method that I talked about before. So, time, yeah. Okay. So I have the shell of something here, just declared a module called sparse mats. We have two choices. We can either implement the sparse matrices module first, or we can implement the Lanczos procedure first, and have a module for that. What do you guys think? I think, yeah, let's make the Lanczos procedure first and have it work on just regular dense matrices. So let's exit out of this, actually, and I'm going to start with Lanczos.f08 module Lanczos implicit none. So I'm not going to go over how Lanczos does what it does, because that's quite complicated. Yes, Flynn, we discussed it at the beginning, but basically there is a Lanczos method for estimating the density of states, or spectral density of matrices. This is most useful for large matrices where explicit diagonalization doesn't go well because it's very expensive. And there is a reference that I had up before that I'll pull up again. So you'll notice reference. So you'll notice that this reference, the paper is from 2016. What I will be discussing, I believe, first was used in like 1993, maybe? If you're unfamiliar, Yusef Saad is a beast in terms of numerical algorithms. Like, he's just an absolute monster. So if you have the opportunity to check out Yusef Saad's books or articles, I recommend it. Okay, so there are a few steps. Step one will be to construct a Lanczos matrix by multiplying the matrix A with a vector multiple times. We'll discuss more what these steps are, but I won't be deriving the full generality of this. This will be implementation based. You can look at the reference I've listed above for details. The second step will be to find the eigenvectors of this Lanczos matrix, which will be much smaller than the matrix A. Step 3 will be get weights from the first components of these eigenvectors. And step 4 will be to write down the density of states at a certain eigenvalue, parameter t. Will be approximately 1 over n, where n will be the size of this Lanczos matrix. Let's see, n by n. Sum from k equals 1 to n. I'm going to write out the numerical formula, and we'll implement it later. M equals 1 to n. These weights and then a delta function t minus theta sub m of k. And we will, I'll define these things. So a sub m to the k equals e sub m k, the first component, equals squared. First component of the mth eigenvector of the n by n Lanczos matrix with starting vector b k. This theta sub m to the k equals the mth eigenvalue of the Lanczos matrix constructed from the kth starting vector. So basically this method will take like m different starting vectors. It'll multiply your matrix A by these starting vectors a few times. It'll do some more algebra to construct this Lanczos matrix. Then we find the eigenvectors. Since we only multiply A with the vector, a few times, this Lanczos matrix will actually be quite small in comparison to the size of A. Then we find the eigenvectors. We get these weights, which are these A sub mk's. And this is the formula for the approximation of the density of states, or spectral density. Now, this algorithm is really cool because when you implement it, nowadays, you can explicitly diagonalize matrices that are like 10,000 by 10,000 on like a home desktop or something, but you'll have to wait like a few minutes or so, even when you're just calling like an optimized out library like BLAS or LAPACK. However, this Lanczos method, so let's see, explicit diagonalization works for maybe 10,000 by 10,000 at best. However, Lanczos, you'll be able to get decent density of states, or spectral densities, for, million by million or bigger fairly easily. Honestly, tens of millions by tens of millions. And, once you guys are done writing, you'll have this for yourselves as well. It's definitely like a thing that most people haven't seen until like they reach grad school. I remember my first year, I learned about this, and like a third year PhD student went up to me and was like, "Oh my god, you know about the Lanczos method?" Like, he didn't learn it until a couple years into his own PhD. But it's very useful for a variety of reasons. Okay. So for this module, let's specify a few things. We're going to make a type called the Lanczos hammer. And we're making a type for this so that people can compare, so that people can initialize multiple different, like, Lanczos procedures with different, like, number of starting vectors or different numbers of iterations. So we're going to have integer number of iterations, let's say 30. We'll have integer number of random vectors equals, let's say we'll start with the default 10. We want the size of the big matrix. Do we? Oh. I don't think we do. We'll see. We'll see. And we're going to have procedures. Pass self. So we'll do construct Lanczos matrix. We'll do procedure pass self get Lanczos eigenvectors and eigenvalues. And we'll want some arrays for actually storing these things. So let's make a real dimension. We'll have it be a 2x2 array, and we'll have it be allocatable. Lanczos matrix. Let's recall what allocatable is. Allocatable means we can allocate memory for it later to have a dynamic size. Hammer time? Yeah. Let's see. So there's what else? We'll want an array allocatable for the eigenvalues. We'll want an allocatable array for the Lanczos weights. We'll also, let's see. Let me check this algorithm here. Okay. So we'll want two more arrays that are allocatable, and we'll call them alpha and beta. Procedure pass self will do calculate density of states, of course, and we'll want like calculate weights, and we can write our own constructors. There's a special syntax for it, but I'm just going to make an initialize procedure. So this module contains and let's see, we'll call it initialize Lanczos process. Subroutine initialize Lanczos process self, and there are a few things that we'll need for this routine. We'll want the actual matrix A, so we'll presume for now that A is a real matrix, intent in A. Remember, we also have the Lanczos hammer. So, then let me correct that typo. So, let's put in some helpful comments, because this is going to be a non-trivial, set of code. It would be good to. Ah, thank you. Lanczos hammer. That's good, right? Thanks, Jacob. Okay, right. We will also want a series of vectors that are going to be our starting vectors. So we're going to make a two-dimensional array called random vectors. And the reason it's two-dimensional, so this is 2D, because we will store n vectors of size of the matrix. Well, the size of one side of the matrix. Okay, so the first thing we're going to initialize is let's make an integer size A. This is a local variable. Size A we'll calculate as the size of A, but we only want the size of one dimension, so of A. So we'll specify that we only want the size along one dimension. We are going to allocate the, what are they called? Random vectors. We're going to allocate the random vectors and we allocate them. If you'll recall with this syntax, we put in random vectors and then we'll put in size A will be the second argument, and what's this called? Num of random vectors. Num of random vectors will be the first argument. So it's, I think, fairly self-documenting, but feel free to type in the chat or speak up if you have a question about what I am typing. So we have the random vectors. We're going to want to initialize these alpha and beta arguments. And by the time that we'll be calling initialize Lanczos process with the matrix A, we're going to know what the size of this Lanczos matrix is going to be, what the size of these eigenvalues are going to be, what the size of these weights in the alpha and beta. So we're actually going to initialize all of these here. And by initialize, I mean allocate. So let's allocate Lanczos matrix. This is going to be, what is it called? Number of iterations. Yeah, num iterations. This will be a num iterations by num iterations size array. How do you tell which way is the dim? So do you mean like whether it's the number of columns or the number of rows? So in this case, it doesn't matter because we'll just make this for square matrices. But dim equals 1. You'll say it can be like number of rows. Dim equals 2 equals number of columns. Of course, that's for matrices. If we actually have tensors with, more than 2 dimensionality, then it gets, more general. Yeah, we'll allocate alpha, and this is going to be as well num iterations. Beta is going to be related. Let me check. I believe this is going to be num iterations minus 2. So we're not initializing alpha, we're allocating beta. And we have a few other quantities, these two, eigenvalues and Lanczos weights. So if our Lanczos matrix is n by n, or where n is num iterations, then the number of eigenvalues will, in general, also be that size. Yeah, as Cronum is saying, you can actually specify like really general things. Like you could specify like that your array is accessed like starting at like 2 ending in 5, or starting at -7 and ending at 2. Like you could do a bunch of things for accessing the arrays, which makes typing some things convenient, but in practice I haven't been using it a lot. Debugging for the whole family. Okay, the last thing to initialize are these Lanczos weights. Allocate Lanczos weights. And let's see. I have a reference sheet in front of me to make sure I'm not messing up, but I think I'm messing up. Let's see. It'll be fine either way. Yeah, it'll be fine either way. I see Jacob is typing, so I'll... we won't be able to tell if it's a good result, so don't worry. Oh, Jacob. That's fine. So this will also be num iterations long. Okay, so you've allocated all of these things, right? Now, this is called initialize Lanczos process, so we might as well initialize the random vectors. Now, all we need to do for that is call random vectors. Or random, sorry, it's like random value, random number, and it's random vectors passed in there. I believe that's the case.
Sorry, what's random number?
Random number is a Fortran intrinsic. It will take an array of basically arbitrary dimensions and fill it with random values between, I believe it's between 0 and 1. So it's actually a Fortran intrinsic. In like C or C++, you have to import a library in order to use random numbers, but not Fortran. It's just inbuilt. What we're going to want to do is make sure our code like compiles at least while we're writing this, to make sure we're not going to have to do a huge debugging session by the end of this. So what we're going to do is, as we craft the Lanczos hammer class and its subroutines, we're going to make sure we are just using them. So what we're going to do is, let's make a Lanczos test file. program Lanczos test. And we're going to use Lanczos. Oh, Jesus, the compiler errors are piling up. Excellent. Hey, this is all a part of programming. And for now, we'll just we'll declare like implicit none, and we'll just start with an arbitrary array with size, I don't know, size s equals 100. We'll have a real dimension s by s array. And type Lanczos hammer. Hammer. That will. Yeah, hammer is fine. I'll call it a density of states hammer. And we'll initialize equals Lanczos hammer right. Let's see. This already automatically sets these defaults. So what we actually want is to use our what's it called? Let me check. Our initialize. Sorry, it's call density of states hammer percent initialize Lanczos process with the matrix array. But we don't want to initialize it with a random array. So let's make sure our array also has call random number array. Okay, let's try that, and I'll look at the compiler errors. I'm sure there are infinity, but we'll go through them. We'll start at the top, and we'll see how to fix them. So we want to start with Lanczos test. No, sorry, we want to start with Lanczos.foh, then the Lanczos test. Beautiful. Many compiler errors. Let's see. Calculate DOS, etc., etc. So these are saying that all the procedures that we gave names for the type, it wants us to actually write out these procedures. So let's take these. I'm going to copy them down here just so we know what we have to do. And we're just going to make like little dummy procedures for them. Subroutine construct Lanczos matrix self. Its class Lanczos hammer intent in out self, and we'll do print. It's a dummy procedure for now. Nah, Jacob. Right. Both will work, but you're right. This looks better. but without the space will also work. Okay, so we're just going to do this for all of these procedures, and I'm going to delete them as we go. So subroutine self. I have some shortcuts that will make me be able to type it faster than you guys. But that's why we pause after a moment. Copy, paste, leave this procedure line. Copy this. Do the same. Admittedly, this is why we write software usually a little more intelligently. Let's copy these two, where we don't write the type-bound procedure names until we are ready for them. Then it's just calculate weights. Subroutine calculate weights, self, copy, paste. Okay, I'm sure there are still compiler errors, but hopefully they're not related to what we just fixed. Okay, let's clear this up. Allocate is neither a data pointer nor an allocatable variable. Let's see. Beta, eigenvalues. I see. Okay. So that's an easy fix. So here we're going to illustrate one of the perks of Fortran. So what it wants us to do is to do this. Self, percent random vectors, self Lanczos matrix, self alpha, self beta, etc. But I'll also show off the associate construct again, which goes something like this. Self percent random vectors. Self percent Lanczos matrix. Let's just try that for now. We'll be optimistic, pessimistic. So we'll try rand vex and Lanczos matrix, and we'll put in the selfs for the rest of these for now and see if they all work. Self percent. So the associate construct, like we talked about last time, allows you to rename variables dynamically, like just within a certain scope, within the scope of the associate construct. And so here, admittedly, we're not really saving ourselves any typing, because if we repeat this process for all of our variables, we would have to just write self percent all of it anyways. But in cases where you use the variable more than once, it might be useful. It's even worse. Oh no. I don't know. I mean, let's see. Has no implicit type. Random vectors has no implicit type. Good question, Jacob. Good question. Okay. Maybe I need to do this. Hold on. First off, I'm gonna move this end associate. Or sorry, no, I'm not. I'm gonna put self percent random vectors down here. I'm gonna let you guys type for a little bit, and I am going to look up the associate construct again. Let's see. Huh. Weird. Okay. Never mind with this associate thing, apparently. So, associate allows us to rename a scalar to be a part of an array, but can't let us rename arrays entirely, which I think is a little sad. But yeah, your abortion plan worked? Okay. That's good. Well, we'll adopt it to self percent random vectors, self percent Lanczos matrix, and let's just eliminate this associate. And we'll try it again. And clear many less errors. Once we put in the selfs, we should be good. Let's see. So we just want to put in self percent here as well. It's actually a little how about this? How about this? Let me try something. You guys can num iterations points to self percent num iterations. I'm going to try this. Aha. Okay, so num of random vectors self percent num of random vectors. When we do this, the errors are gone. Yeah, the code is a with all the selfs, it's actually pretty ugly. So here, with this extra associate, for the scalars at least in the problem in the system, for the scalars, num iterations, and num of random vectors, then the associate helped clean this up a bit, so that only the arrays we had to use the self access for. I'm happy. We were able to use associate still, even if not in the full generality I wanted to use it. Amen. Typos. Typos hurt. Whew. Again with the implicit types. Dang it. So if you want to paste your error screenshot, feel free. It's probably just like, let me look. Random vectors. So that one you'll have to do self % random vectors for. Like here, call random number, self % random vectors. And that's because we have to use the self % for these arrays in the class. But yeah, try that. Try just putting self %. And that should work. Good. Yeah, that is definitely not the syntax. So let's look at, what is it, Lanczos test. So instead of like the Python syntax where you do array equals like random number or whatever, numpy.ran, you just call the random number function and you put in what array you want to be filled in. Array will be filled with random values. No worries. So when I made sure, let's see, my code compiled, which means this initialize Lanczos process works now. Now, admittedly, this is a lot of stuff to allocate. But we're done with the allocation part of this business. So, done. Now, we have a few more procedures to actually implement. Oops. Now, we don't have to write them in order. We can go from like easiest to hardest. So let's start with calculate density of states. So we'll start with, we'll work on calculate density of states next. Because once we have all the other calculations done, this part is actually fairly easy. So this will use the Lanczos weights and accept a user input array of for the spectral range, which is what values they want the spectral density to be calculated on, as well as the user's density of states array. So let's put these in. So we'll do spectral, let's see. We'll do spectral domain. So I guess instead of spectral range, we'll do spectral domain in this comment. And density of states. Okay, so the spectral domain will be a one-dimensional array. So real dimension just 1, intent in spectral domain. However, the density of states, it'll still be a one-dimensional array, but it'll actually be the intended output of this calculation. So, instead of it being a subroutine, we can make this a function. However, let's see. We could make this a function. However, if you're going to be calling this calculate density of states routine multiple times, having a pre-made density of states array to be filled by this subroutine will save you the memory allocation costs. Oh, no worries, Jacob. It's cool that you stayed as long as you did. I'll be honest, this is probably going to take a while. So we could either just call it quits. I could continue. Yeah, we've been going for 2 hours. That is fair, Flynn. The algorithm is in the paper that I posted as a reference. Or I could keep going and just record the rest of this session and just post come to seminars, get homework. Very true. Either way, I'm going to finish this, but then I could post the reference implementation. Okay. So for Discord's sake, I guess I will cut it off after we finish this density of states procedure. We'll call it there, and then I'll keep working on it and post a reference implementation, and like we'll have it. Then we'll have it. You guys can try it yourselves. So let's finish off this density of states thing. So if we look above to my steps, we'll note step 4 is the one where we get the density of states. Now n here, n is actually going to be the number of random vectors. So that's this n. M is going to be the number of iterations that we had. So these are all numbers that we have. A sub m to the k, or a sub m k, are numbers we haven't computed yet. Same with theta mk. But we can assume that we have them for the purposes of writing this procedure. Don't worry, Jacob. It'll be like, a few lines. So if we associate n to self percent, what was it? Number of random vectors. Let's check the syntax. Okay, don't say out the full word number. And we have m being the number of iterations. We know this will work because these are scalars. Let's put in the self percent. Let's see. So we need to make a couple local variables for the indices in the problem. So integer, we'll do k and m. And we're going to have 2 loops. So do k equals 1 to n. So this is loop over random vectors. And this is iterations. Do m equals 1 to m. See, the self-documenting code part of Fortran, I think, is pretty cool. Naming these do loops. Let's see. So we want what are we going to assume about the density of states? This is a question. Do we assume density of states is initialized to 0 or not? I'm going to assume no, it's not initialized. So let's make sure that the density of states is initialized to 0. And let's see. Gosh. I might have to change this up a little bit, actually, with how I've implemented it. Yeah, I'll have to change up part of this. Okay. So we'll go up to Lanczos weights and eigenvalues, and we're going to make them also arrays of random vectors iterations. So this is the allocate statement, and this is because we're going to have a set of eigenvalues for each starting vector in this Lanczos density of states calculation. So we'll want to allocate them as arrays, and we'll want to initialize them or declare them as arrays, which will be up here, dimension 2 by 2. And once we do this, once we make these changes, we will be able to go down here and just do the density of, let's see, we'll need one more loop. We'll do spectral index. And we'll need to do density of states domain loop. Yeah, that'll work. Do spectral index equals 1 to the size of the spectral domain. And let's indent all these and make sure we have an associated end do. We'll add, yeah, no problem, Flynn. We'll add a real integer that we'll call, or a real number that we'll call t. We'll make sure t is equal to spectral domain of spec index. And this is what's going to go into our delta function. And we're just going to do density of states at the spectral index equals the density of states of the spectral index plus self percent Lanczos weights km times delta of t minus self percent eigenvalues km. Now this is basically the formula we had above in step 4. But the problem is, we don't have a definition of delta in the program. So we can do one of two things. We can just approximate it, and we just add 1. We do an if-then statement where if t equals one of the eigenvalues, we add 1. Alternatively, we, instead of using a delta function, what we do, and what's done in the paper, is we do a Gaussian instead of a delta function. Now we still have to write a function for the Gaussian, but let's do that. Function Gaussian of x, and it's just, it's not of x, it's, of x results g. real intent in X and real G. And anybody remember the expression for a Gaussian? Let's see, it's what, 1 over 2 times 3.14159, 1 over 2 pi times the exponential of like negative x squared. Now, we actually want to have like a standard deviation. And so we're going to have like divided by something called sigma squared. But sigma, we're not going to have it be passed in by the user. We're going to define sigma on the module level. So in the module level, we're going to have real parameter sigma equals, I don't know, like 0.001. And so this is just going to be a broadening for this Gaussian function. And I believe we'll need to look it up. We need to include sigma like in this denominator somewhere. Yeah. We'll need to put sigma in this denominator. Sigma times this. And then we have our Gaussian function. We have our Gaussian function. We have our density of states calculation. We haven't computed these Lanczos weights yet, or these eigenvalues yet, but we've done, like, you know, the beginning initialization, and we have what the ending is expected to look like. So with that, let's just see if this, is there a square root missing? Good question. If I look at the normal distribution, I see that it says we should have a square root acting on the 2 pi, and that there should be a negative 0.5, so a 1/2 multiplying this. Does that look better, Vi? We're assuming mu is 0 because of the way we're calling the Gaussian. Because we're calling this Gaussian like this up here, t minus the specific eigenvalue. The way we're calling it makes mu 0 here, but other than that, it seems like that seems good to me. Let's see if it compiles, and if it does, then we'll call it good. And it does. So we're like 30% of the way towards implementing a paper. At least one of the algorithms, you know, discussed in this paper. It discusses a few different algorithms, but the Lanczos method is the best among them. That's the conclusions of this paper, anyway. Anyone have any questions before we go off and I stay here and program this? And then later post it in Whiteboard or seminars, probably seminars. How does the associate look? This part. All right, Emacs. Emacs, behave, please. Okay. So it has this syntax. By the way, in Fortran, you can force an end line and continue on the next line by using this ampersand. The ampersand way makes it more readable when you have quite a few different objects being associated. But like this is the kind of programming style that's here, I'll even delete this dummy procedure print statement. This is the kind of programming style that I think is pretty good. Like that Fortran allows us to employ. You know, we've got this temporary associate for these scalars. We have array indexing, you know, natural array indexing with K and M here. We've got literally a function called function. You know, it's a Gaussian. It just returns the Gaussian function. Ah, yeah, missing bracket. I see. But Vi, did you get the associate part for your question? Did you mean this associate? Okay. Yeah. Basically, every construct in Fortran has an end. See, in Emacs, I can delete this, right? I can do Control X, Control W. No, sorry, Control C, Control W. Yeah, Control C, Control W. And Emacs in its Fortran mode will just put the end appropriately. I love Emacs. Oh, Emacs. Okay. Any other questions? All right. Well, thanks, guys. Yeah.
Thanks, dude.
Hope you guys learned something. Yeah, I mean, do you think it'd be worth me recording the rest of my creation of this, or do you think just posting the representation or implementation?
I think that
No, I would.
It is some extra concept. Not necessarily the whole thing.
Fair. If I look up at this stuff, so I think it might be worth recording some of it, because if you look at step 2, find the eigenvectors, this is we'll have to use LPAC or BLAS or like some other library to find eigenvectors of this smaller matrix, which is a non-trivial thing to do.
Installing libraries.
Not installing libraries, but like the LPAC, the BLAS LPAC syntax is kind of awful, like for a beginner. Because they did Fortran when like they made these libraries when Fortran was old and had terrible syntax. So this step 2 is probably like the one where having a recording might help, just because the syntax, but maybe the reference implementation would be fine. No, I think I'll just make the reference implementation.
Maybe it's up to
Yeah. Okay. I'm going to go have some lunch, though. Thanks, guys, for participating. The reference implementation, I'll try and get it up like today, tomorrow-ish. It won't. It shouldn't have anything new, like in terms of learning Fortran, other than the calling LPAC or BLAS, and you'll have to compile it a certain way. I'll share how to do that. But other than that, like I've shared basically all of the Fortran things that I care about in Fortran. There might be a couple like bits and bobs, but overall, that would be a part 3, Vi. And I would probably not talk about MPI. I would talk about coarrays, which were introduced in Fortran 2008. They're basically the Fortran standard version of MPI, but easier to use on the user. Yeah, that would all be like a part 3. CUDA is, how to use graphics processors for doing like big computations. Yeah, ML or anything. Sorry, there's something called coarrays in the Fortran 2008 standard, where basically you define arrays with a certain syntax that makes it clear that different processors will be dealing with different parts of an array or different slices of an array or something like that. And it's easier syntax than MPI. But I am not getting into the details right now. CUDA, I think, is pretty cool in Fortran. As you can tell by my username right now, I am in love with CUDA Fortran at the moment.
So CUDA is not. It's not
CUDA is a framework for programming GPUs. It's for NVIDIA GPUs. So, in order to use CUDA, you need a compiler. Well, in order to use CUDA for like Fortran or C, you need a compiler, a special compiler. So it's not just an API. Like it is, but you need the compiler to like compile it in, because NVIDIA has CUDA being closed source and all.
So it's basically on the same level as NGO working back.
No, it is not lower level than that. It's another API, but actually it's maybe a little higher level. I've heard that CUDA is easier to use than OpenCL and OpenGL. Yeah, CL probably. Like CUDA, Fortran, or just CUDA in general, the basics of it is fairly simple. Could probably cover it in like an hour, maybe less. But the how to actually write good CUDA code would take like a couple hours, maybe more. Yeah. Yeah, no problem. I'll in the seminars channel when I finish this implementation, I'll like upload it. I'll upload like a test, and I'll tag you guys.
Nice.
Yeah. All right. I'm gonna get going.
Thanks, dude.
Yeah. Maybe there will be a part 3 with MPI and CUDA and stuff.
I see you.
Bye. I see, Vi, you're still typing, so. Yeah, we're done. Goodbye, everyone. I'll start recording. Jacob, when do you think we should start? Should we wait for, like...
Yeah, give it a couple.
Yeah, makes sense. We'll use whiteboard for people to communicate to me during the seminar. So, yeah, this will be a Fortran seminar. We'll get started in a couple minutes.
So, you know, like, you actually like fully customize your chip text that it with like some build system already set up for.
Well, you see, I don't need to do that because Emacs comes with something called an F90 mode. So, Emacs, when you download Emacs, it'll come with like a bunch of what are called major modes and minor modes. So, for example, I opened this, Fortran document, and Emacs said, "Oh, the file extension is like .f08. You're using a Fortran file. Let's highlight the text in a particular way, like using this F90 mode." So I can disable the F90 mode. Well,
I mean, more like it says like competition and stuff. Just highlights like some extras.
oh, I see. So I could get that set up, but I don't currently have that set up. I'd rather it still be at least mostly followable by the people watching.
Oh no, I mean for yourself as a part of the
Oh, that's a good idea. I don't currently do that, but I could. Particularly because in Emacs you can, as you said, you can customize different macros pretty easily. I can even run the bash terminal while inside of Emacs, which is, I mean, it's fun. I've done Python while inside of Emacs, just run a Python instance.
Oh, that's the server together.
Yeah.
Oh, nice. I think I was page second don't have any
Maybe. I think Hank was interested in the first one and missed it.
I mean he was in
Yeah, I saw that. Yeah. For today's seminar, I will be writing in Emacs. Last time I wrote in Nano, so that people could more easily follow along. For the people who want to, or who know Emacs or want to try it, I have the shortcuts in the bottom left. The important shortcuts, which is saving your file and quitting. Okay. It's been a few minutes. Should we get started?
up to you.
All right. Yeah, I will get started. I've already been recording, which is nice.